Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 2-4, Scatter Plots, Correlation, and Regression. In this lecture, we're going to start with a review of scatter plots, which we saw in the previous sections in this chapter, and then we'll move into talking about correlation and the linear correlation coefficient. That will segue into a discussion of critical R values and P values, and then we'll wrap it up with a brief discussion on linear regression. So let's get into it. Key concepts in this section. We're going to introduce the analysis of paired sample data. So essentially what we have are two variables that are paired together. We're looking for a relationship between the variables. Scatter plots will of course play an important role in our analysis of two variables. As we've already learned, the first thing you should do when you're analyzing any potential relationship between two variables is make a scatter plot. Of course, linear regression analysis also involves correlation and the linear correlation coefficient, which we'll discuss later in this chapter. We're going to briefly touch on linear regression here, but keep in mind that we're going to return to linear regression when we get to chapter 10, and there we will discuss linear regression in much more detail. For now, we're just going to focus on how to determine the equation and the graph of the straight line that best fits our data. So to start off with, let's look at a review of scatter plots. As we've seen previously, scatter plots simply plot paired data on a horizontal and vertical axis. So you've got ordered pairs of x, y coordinates, and you basically plot your data on a plot. These scatter plots can reveal potential relationships between two variables. So in the graph on the left, you see that the plots are forming more or less a straight line. It's actually pretty curvy, but you can see the pattern is more or less roughly a straight line. So we could say that there's a potential relationship between number of users and the amount of memory that they use. However, the graph on the right has what I call the shotgun effect pattern because it looks like someone fired a shotgun against the wall. There's no discernible pattern here. There's just a bunch of data points that are scattered all over the place. So in the graph on the right, we would say there's not likely a relationship between quality and price. Let's talk for a little bit about correlation. So correlation between two variables simply means that the values of one variable are somehow associated with the values of the other variable. Keep in mind what we've said repeatedly before. Correlation is not causation. Just because there's an association or relationship between two variables, it does not mean that one causes the other. Correlation is not causation. There are many different types of correlations that follow different types of equations in mathematics. The simplest type of equation that we have is one that has two variables and represents a straight line. So a correlation that corresponds with a straight line is what we call a linear correlation. And what that means is that our two variables are correlated such that the plotted points of paired data result in a pattern that can be approximated by a straight line. Let's look at an example to illustrate. Suppose we're looking at a relationship between weight and pulse rate. So the first thing we do is we look at a scatter plot, which we see here on the screen. Now, correlated variables will form a pattern on your scatter plot. This is why the first thing you do when looking for an analysis of two variables is make a scatter plot, because you're looking to see, is there a pattern that would indicate a relationship? Here we have what you might consider to be a shotgun effect. No real discernible pattern, just a blob there in the middle of your graph with some scattering points around the center point where most of the data is collected. So yeah, there's no real pattern here. And so therefore, the lack of this distinct pattern suggests that we don't have a correlation between weight and pulse rate. And when you think about it, that makes sense. There's people of all different types of weight that have all different types of pulse rates. So we wouldn't expect a relationship between those two variables. Again, this is what I call a shotgun effect because it looks like the pattern left by a shotgun fired on a wall. Here's another example, waist and arm circumferences. So here we do see a more distinctive pattern of the plotted points. Not exactly what you would call a straight line because of the axis on the graphs makes it look more like a band range that you're actually fitting the data into, but that range follows more or less a straight line pattern. So we would look at this and say that, yeah, there probably is some association between these variables, and so it's worth looking into in more detail. Of course, how do we measure the strength of that correlation? Well, that's a horse of a different color, as they say in the Emerald City from The Wizard of Oz. And if you've never seen The Wizard of Oz, you really need to get up to speed on your classic film education, because it is a classic film and it's inspired American culture, and you really need to gain a comprehension and appreciation of that. Plus, it's just a good movie, and there's lots of good songs in the movie. So if you like musicals, you're really going to love The Wizard of Oz. So go check it out if you haven't watched it. Let's talk about the linear correlation coefficient, because this is how we're going to measure the strength of a linear correlation between two variables. Now, there's different denotations or symbols used for the linear correlation coefficient. The author of your textbook is using a lowercase letter r to denote the linear correlation coefficient. However, there are others, and apparently StatCrunch is among those others, that use a capital letter R instead of a lowercase letter r. It really doesn't matter which you use. Just understand that you're going to see different denotations from different sources, and it doesn't matter because we're all talking about the same thing. So whether it's a capital letter R or a little letter r, we're talking about the linear correlation coefficient. The value of the linear correlation coefficient is always between -1 and 1. So you'll never see an R value that's greater than 1 or less than -1. Here on the bottom of the screen, you're seeing something of a scale that helps us to decipher or interpret the meaning of the linear correlation coefficient. So the closer we are to 1, the more we have a perfect positive correlation. So strong positive correlations are going to approximate 1 or get close thereto. The closer we get to -1, that just means we have a perfect negative correlation. So the closer we get to -1, we're going to have more strongly negative correlation. Now, positive or negative simply describes the slope of the line of best fit. Notice how we have perfect positive correlation here on the left, and notice how the points, the data points on your scatter plot are assembled in what would be a line, and that line has a positive slope because as you go from left to right, the line goes up. So that's what we mean when we say positive correlation. That line of best fit has a positive slope. Over on the other extreme, -1 for R value, we have perfect negative correlation, and that just means the line of best fit has a negative slope. So as we go from left to right, the line of best fit will go down. Notice in the middle, we have 0, which is directly between 1 and -1. Here we have absolutely no correlation whatsoever. So the closer our R value is to 0, the less correlated our variables will be with each other. So, just to review, a value of R close to -1 indicates a strong negative linear correlation. A value of R close to 0 indicates a lack of linear correlation. And a value of R close to 1 indicates a strong positive linear correlation. Let's look at an example involving shoe print length and height. So law enforcement has always been interested in knowing if they can estimate the height of a suspect by measuring the length of shoe prints left on a crime scene. Oh my gosh, that's like a total typo there. It's not show prints, it should be shoe prints. I'll have to fix that. Anyway, shoe prints are what we're talking about, because shoe prints are evidence that are left at the scene after the suspect flees. Whereas, if you ask witnesses how tall was the suspect, you're going to get a variety of different answers, because people's memories are a little different when they're asked to remember something like a crime being committed, or the scene of an accident. So it's really helpful if we could estimate the height of a suspect just by measuring the shoe print that's left on the scene. So there's a junior team member on the forensics team that's looking to investigate whether a correlation exists between shoe print lengths and height. So this individual measures 5 associates, they're in law enforcement, and then looks to do a small statistical analysis to see if there's a relationship. So here's the data set that was collected. So you see here's the 5 shoe print lengths that were measured and the corresponding heights of the persons who left those shoe prints. This is an example of what we call paired data, because for every value of shoe print length, there is a unique value of height length. Although I shouldn't say unique length. There's one that actually goes with. There's actually one that actually goes with each one. So there's one X that goes with each Y and vice versa. So what's the first thing you should do when analyzing a data set with 2 variables? I hope you said make a scatter plot, because I don't need to give you much time to actually come up with the right answer. We've gone over this so many times. It should be like second nature. Make a scatter plot. So when we go to StatCrunch and do that, here's the scatter plot that results. So we see our 5 data points, and sort of a straight line here, and maybe less of one here, but you know, you've got these 2 points that are kind of way out far from each other, and so that's going to have an effect on our line of best fit, and also the linear correlation coefficient, as we'll see momentarily. What pattern do we see in this plotted data? Well, as I just got done saying, we don't really see much of a pattern. It could be a straight line if we didn't have these 2 points so far apart from each other, but you know, there really isn't much of one since we do have those 2 data points, and so that's what we have to live with. Is that what the linear correlation coefficient will tell us? Well, let's find out. So often what we'll do is use a statistical software package to calculate the value of R. This is the glory of living in the 21st century. We get to let technology do all the hard work for us. I can remember when I was in college, I did a lot of this stuff with the hand calculation. Oh, it was painful. So you should feel fortunate that you live in the 21st century to where you don't have to do that. Although if you do want to go old school, I'll teach you how to do that. But for right now, let's just glory in being in the 21st century and use technology. So we're going to use StatCrunch to calculate this for us. And when we do, we get a simple results window that looks something like this. So there's a whole bunch of information here. But essentially what we're looking for with our R value is located right here. So up here near the top, it says R. And notice it's a capital R, which is different than what the author of the textbook uses. But it still says correlation coefficient, and then it gives you the value, 0.84573297, which we could round to say 0.85. Now, what type of correlation, if any, does this value indicate? I'll give you a moment. You should know this because we just talked about it. Well, if you said a fairly strong one or something thereabouts, then yeah, look at 0.85. It's not far removed from 1, and it's certainly a lot closer to 1 than it is to 0. So we would say that's an indication of a fairly strong correlation. However, as we'll see in a moment, there's actually a more objective means of statistically indicating a correlation between 2 variables. First, though, I want to show you what visually we see in the scatter plot when we add the line of best fit with the data. We get something that looks like this. So notice that 0.85 means that our data points are actually somewhat close to the line of best fit. Of course, notice the scale on your axes. Scale is pretty small, so these data points are actually pretty close to the line, even though just looking at the graph itself, it looks like they're a little distant from the line. But when you look at the scale and see how small it is, you realize, yeah, we're really not that far apart from the line of best fit at all. Okay, so critical R values are how we're going to statistically determine whether a correlation exists or not. Because, I mean, looking at how close a number is to 1 or -1 is kind of subjective. And in many respects, it's kind of like when we were looking at the histograms and trying to figure out, okay, we'd say that this is normally distributed data, and we try to look for that approximate bell-shaped curve. But the more objective means of assessing normality is with a normal quantile plot. So we have a similar situation when assessing correlation. And the equivalent of the normal quantile plot for correlation is the critical R value. So essentially what we have to do first is calculate the critical R value, and then we compare it with the R value that we get from our data to determine whether or not we have a correlation between our two variables. Critical values help us to do that because they mark the boundaries between regions of correlation and regions of no correlation. So every value of R has associated with it two critical values of R. One is positive and one is negative. And those values are determined by your sample size. So supposing that we have a number line here that goes from -1 to 1, because this number line will then contain all the possible values for R. Remember, R can't be greater than 1 or less than -1. We have two critical values, one that's positive and one's negative. And those values are located somewhere on that number line between 1 and -1. Now, the critical values form a region of non-acceptance, meaning that within this region, there's a correlation between the two variables that does not exist. So this is what we call a region of non-acceptance. So if our R value lies in this region here between the two critical R values, then that means we're going to reject the idea that our variables are correlated because there is no statistical evidence for correlation. If our R value is inside that region of non-acceptance, just as I said, your two variables are not correlated. However, if the R value you obtain is outside that region, so if we're here in this region here on the negative side, or here in this region here on the positive side, then our two variables are correlated. You'll notice that the author of your text and working problems for homework talks about positive and negative tails. And really what she's referring to are distributions, which we're not going to start talking about until we get to chapter 5. So I'm a little surprised that he's actually talking about using that type of language here in chapter 2. That being said, it's easy to figure out what he's talking about. So when he talks about a positive tail region, he's talking about this region here on the right. That's where your R value is greater than your positive critical R value. Likewise, there's a negative tail region on the left where the R value that you have is less than the negative critical R value that you have for your given sample size. Let's look at an example to illustrate this concept of critical R values. So suppose we have a researcher that's monitoring the growth of bacteria in a Petri dish, and the data that this researcher obtains we have listed in the table. So each day the researcher goes and counts the number of bacteria in the Petri dish. So on day 1 we have 30 bacteria, and on day 2 we have 45, so on and so forth. So we have a linear correlation coefficient R for these data, and that value is 0.8999. So the questions we're asked are, what are the critical values of R, and what can you conclude about a linear correlation? Well, the easiest way to find our critical values of R is from a table, and we're going to use sample size to determine from the table what our critical values are. Now, you'll notice in your homework problems that ask you about this, you can see a little book icon like you see on the screen here with the instructions. Click the icon to view the table of critical values of R. When you do, you see a table pop up that looks something like this. This is a table that we're going to use to calculate our critical R value. Actually, the values are already calculated for us. We just have to decide which one's the right one. And the way we do that is by sample size. So looking at the number of pairs of data we have in our analysis tells us what our sample size is. So in this example, we have a sample size of 7 because we have 1, 2, 3, 4, 5, 7 pairs of data. So now we're going to use the table to find our corresponding critical R value. First, we look on the left to find the number of pairs of data. What's our sample size? It's 7, and that's located here. So then we look across on the other column of the table to the corresponding value, and we get 0.754 as our critical value of R. But remember, we have two values of the critical value of R, so therefore we would input plus or minus 0.754. Remember, one value is positive and one value is negative. So you can put this in as plus or minus 0.754, or you can put it in as negative 0.754, comma 0.754. Either way, it should give you points for giving a correct answer. So there's our answer to the first question. What are the critical values of R? But how are we going to answer the second question? What can you conclude about a linear correlation? Well, now that we know what our critical R values are, we can compare those with the R value we get from analyzing our data to make a conclusion about correlation. The first thing we're going to do is stick our critical values of R on a number line. So remember what we learned earlier. Here we have our critical R values where one is negative and one is positive, and in between those R values is a region where we don't have any correlation between our variables. On the left side, if we go less than the negative side, that's the left tail that the author would reference. That's a region of negative correlation, and then greater than the positive R value puts us in a region of positive correlation. Well, our R value that we calculated that was given to us in the problem statement, 0.8999, that's located right here in this region of positive correlation. So it's in the quote-unquote positive tail of the distribution, so to speak. And therefore, because it's in that right tail above the positive value of R critical, there is sufficient evidence to support a claim of linear correlation. If we found that we were inside this middle region here, in between our critical R values, then that would mean that we do not have sufficient evidence to support a claim of linear correlation. There's another way to go about supporting the claim of correlation, and that is with something called the p-value. Technically, the p-value is the probability of getting, by random chance, a value for R that is at least extreme as the one obtained from your sample data. That's a really highfalutin statistical definition, so let's break it down like a fraction for you. As a general rule of thumb, your p-value is going to be somewhere between 1 and -1, just like you would get with the R values. As a general rule of thumb, if your p-value is above 5%, then that's considered a high p-value and you're within a region of non-acceptance, which means you don't have correlation. Conversely, if your p-value is below 5%, then you have what's considered a low p-value and you are within the region of acceptance, which means you have correlation. Usually, if you're not given a p-value, you can use statistical software to find them. And we'll actually be doing that later when we get to chapter 10 and talk more about linear regression in more detail. For the moment, I believe your p-values will simply be given to you. So you don't have to calculate them in any way, you just have to know how to use them. Let's go back to our shoe print data set. The p-value for that data set is 0.071. This is the same as 7.1%. So if you just take that decimal point and move it 2 places to the right, you'll convert the decimal to a percentage. And so if you're asked for a percentage in a question on your homework, this is how you would get the percentage, 7.1% in this instance. So we then compare that with our 5% rule of thumb value, and because 7.1% is greater than 5%, that means we have a p-value that's considered to be high, and so there is not sufficient evidence to conclude that there's a linear relationship between shoe print length and height. However, if we go back and look at our data set for bacteria, we find a very different story. So the p-value for that data set is 0.006, which is the same thing as 0.6%. So we then compare 0.6% with our 5% rule of thumb, and because 0.6% is less than 5%, the p-value is low, and so therefore there is sufficient evidence to conclude that there's a linear relationship between the number of days and the number of bacteria. Let's briefly touch on linear regression. So linear correlation coefficient R is describing the strength of your correlation. But another way of looking at that is saying it describes how well a single straight line fits your data. We call this line of best fit a regression line. Now, because of the way that this line is calculated, we also can call the line of best fit or the least squares line. These are other names for the line, but we're all talking about the same thing. It's the regression line. So the regression equation, the algebraic equation that describes this line is listed here. Y hat equals B naught plus B1 times X. In this equation, B naught is the y-intercept and B1 is the slope of the regression line. And again, statistical software packages often, give these values to you. StatCrunch is no exception. So if we look over here in our scatter plot, along with our line of best fit, we can actually use StatCrunch to give us the equation of this line of best fit that you see here in red. So here's an excerpt from the results that we looked at earlier. We're looking at the top part of those results. And if you look right up here at the top, here's the actual regression equation for that line of best fit. StatCrunch has computed it for you. So you just take the values and run with it. B naught, which is your y-intercept, is 122.17, and the slope of your line, B1, is 1.84. You can round these numbers off to however many number of decimal places you're asked to do so. 2 is pretty common if you're not asked for anything, but if you are asked for something, make sure that you round to the appropriate number of decimal places. And that's pretty much what it is. Which brings us to the end of this lecture. So if you have any questions, send me an email or come talk to me in class. Otherwise, I will see you in the next video. Thanks for watching.